We are launching our inaugural address of Geeks on Parade or whatever. All right, so we're going to try to graph this and see what the volume is. This is a volume problem. A volume that is generated by rotating. Okay? And this, in this particular case, this is going to be the first one that we're going to try to rotate, not about the x-axis, but about the y-axis. So a good first step is to maybe take a look at the picture, the 2D picture, and see if we can sort of figure out what the shape of this is going to be. So let's start with the easy points. Y equals 1 and y equals 3. So let's move this up a little bit. So y equals 1, there's going to be a line there. And y equals 3. And we'll try to make these lines straight. All right? And then, of course, we're going to make our axis of rotation, the y-axis. It's not recording? Oh, no, that's me whenever I push the button here. But it may not be. You might be right on. So we're going to rotate it about the y-axis. So, in general, what we're looking at is the radius is going to be perpendicular to the y-axis. So we need to take a look at this curve 1 over x. So, well, if we're going to rotate it about the y-axis, instead of having the function in terms of y, we might find some benefit in finding this same graph in terms of x, right? So what would this equal if you were to solve for x, in other words? Okay, perfect. X equals 1 over y. But 1 over x is just going to look like what? As x gets bigger, let's take a look at this one. As x gets bigger, what happens? The fraction, oh, right. Yeah, it gets closer to 0, right? So, in fact, it's going to do something like this, right? And eventually, it's going to dip below this y 1 line. Whoa. All right. So much for my artwork. So, this is just the area that we're interested in. So let's see if we can highlight that. That would be this area right here, right? Yeah. Okay. All right. So, we don't really need this area over here so much. Now, if it's going about the y-axis, remember the volume formula is what we're eventually getting ourselves into, right? And in general, pi r squared times the height is the volume of a cylinder, right? So in this case, if we think of the radius as being the distance that this curve hits as it hits the y-axis. So what do we call this little strip right here? Okay? Yeah, that's the radius, but the width of that is dx. But in this case, since it's touching the y-axis, it's actually dy. So that's why we're going to use x equals 1 over y as our function. But what's our limit of integration on this? What do you think, Martin? The question is, what's our limit of integration? Yes, now we're going on the y-axis, right? So if you're talking about taking the integral with respect to y, obviously we're going to have dy, right? And so this is y equals 1, and this is y equals 3. And, of course, we could take our pi constant out. And then our radius squared is just the length of this red line that we've drawn here. Yeah. Because of... Okay. The question was, why are we using 1 and 3 And the answer is, okay, good. So we're just going to put this 1 over y. Now everything's in terms of y. The limits of integration from 1 to 3, the function in terms of y, and this is our height of the little disk. All right, so now it's just a matter of doing the algebra on this, huh? So probably keep the current, but ask me again. Why don't you ask me every 5 seconds? Don't show this message. There we go. Yeah, it will happen. So 1 over y squared. Well, let me just write that y to the negative 2. Now this becomes a pretty manageable problem. So what's this integral? Okay. Negative 1 over y, because that becomes negative 1. And we just need to evaluate it between 1 and 3, and then multiply that answer by 5. Okay. So I'm going to stop the recording here, just because.